Let's now talk about data sampling with a sliding window. So what that means is previously we talked about creating these subword tokens from a given text, and then we converted the subtext tokens into token IDs. And later we will learn how to convert them into vectors, embedding vectors, and then pass them to the LLM. But for now, the focus is really still on this part here. How can we do this efficiently? For instance, the LLM, it can't receive all the tokens all at once as input. So the topic of this section is how do we provide smaller chunks of these token IDs to the LLM efficiently so that we can later train the LLM efficiently. So let's go to section 2.6 here. There's one more thing I wanted to mention before we go to the code examples. LLMs, essentially one of the hallmarks of LLMs is that they are predicting one token at a time. So if we have an input text, for example, LLMs learn to predict one word at a time. If that is our input text, let's consider the first token. If we pass only this token, ideally the LLM should predict the next token. And here in the next row, LLMs learn the next token is 2 and so forth. So the goal is to teach the LLM to predict one word at a time. And this is one of the interesting things about LLMs. This makes them so efficient at scale in terms of being able to train them on very large data sets. In traditional machine learning, we usually as humans had to find ways to create labeled data. So here it's actually very easy because we can use raw text and the label creates itself by just being the next token. So we are just taking text, we hide part of the text. For example, here we hide this text, we provide one token as input, and then the next token is the target label that the LLM learns to predict. We will learn more about how this works, for example, optimizing a loss function, predicting next tokens, and so forth in later chapters. Here, the goal is to just prepare the data in a similar format so that when we pass an input to the LLM has then the next target that it can predict. So if I go to my code here, so what we are going to do is we are going to do this efficiently for the verdict data set. So just to provide it here again, the verdict was the short story by Edith Wharton that we downloaded earlier. And what we're going to do now is we're going to use the tick token tokenizer to encode this into token IDs. And if we do that, we can see we have 5,145 token IDs. So just maybe to visualize them, you can see them. So these are all the token IDs in our text. And now the goal is how can we provide them efficiently to the LLM in the form of sub chunks. So you can see it's a lot of tokens and the LLM wouldn't be able to pass them all. So we want to, for example, provide chunks of 4. 4 because it's nice and small and fits into this Jupyter lab when we visualize it and I can make nice figures. But in practice, the chunks are usually much larger. They're usually 1,000, 4,000, 8,000 tokens at a time, depending on the LLM. Here, in the case of GPT-2, I think it was 1,024 tokens that were used at a time during pre-training. We are, in this particular notebook, only using 4 for visualization purposes, just so that I can show you some things more efficiently in a figure. So that is what I wanted to say here. And we are also going to use a particular subset. We are truncating the first 50 tokens just to have some nicer examples and some nicer text. But this is just like an implementation detail to make this visually a bit nicer. Now, what I wanted to show you now is the way we prepare the X, the inputs, and the Y, the targets. I kind of showed it to you here already that we are concerned always with the next target token here. So we are creating a data set here where the targets are the inputs shifted by one position, which then helps us to have the targets as the next token to the LLM. So for instance here, what I'm doing is I have this sample text. So the sample text is, it should be about 5,000 something. Tokens. So 5,095 tokens because I just truncated some tokens. So you have 5,095 tokens. and we have a context size of 4. So we are only considering 4 tokens. So here we are going to take the first 4 tokens, and then we shift it by 1 position so that the targets are shifted by 1 position. So you can see it here in the output. We have the inputs, and then the targets are shifted by 1 position. So if I show it like this is how it would look like, but it's a bit hard to read. So I inserted this white space so you can see where the overlaps are here. So you can see those 3 tokens overlap, and this would be the next token, and this would be the previous token that is not presented in the targets. So if the LLM receives this token, it's supposed to predict this token. If the LLM receives those tokens, it's supposed to predict this token. If the LLM receives those tokens, it should predict this one. And if it receives those, it should predict this one, and so forth. So that's the whole idea here. And maybe to make this a bit more clear, what I've just shown you visually. So here's some other code example, which is exactly doing what I just showed you, where it's showing the next token. And since this might be a bit abstract with these numbers, we could also just use our tokenizer. For example, let me copy this so it's easier than just retyping it. So we can use our tokenizer to decode the token IDs back into text, and do this for both the targets and the input context. And so this is the same. Oops, made a mistake. I probably forgot to close parentheses. So you can see what it would look like. So we are always predicting the next word in the sentence. And so to make this really efficient, we are going to use PyTorch, where PyTorch is a very popular deep learning framework. It's probably the most widely used deep learning framework today. And so we're going to import this and use the data loader and data set classes from there, because they implemented this very efficiently, and we're going to reuse these parts because they're not really part of the LLM. We are still talking about setting up the data set, and it would be a bit, tedious to reinvent the wheel and write our own data loaders and so forth. And so for that, we are going to use PyTorch. And so PyTorch is imported as torch, even though the library is called PyTorch. It's just a convention we have to remember. And if you followed the video in the first chapter, I showed you some setup tutorial. If you follow this and install the requirements.txt, this should already work. In case it doesn't work, it means you don't have PyTorch installed. And so one way to install it would be uv pip install or pip install, depending on how your system is set up, and just typing this command, and it should automatically get a good version for your computer. However, if you want to be more specific, for example, you can go to pytorch.org, and on this website, they have like this installer menu that has different commands for different computers. So for example, I'm running this on a Mac with pip, and then it would give me that this command. If you are on Linux by default, here this would be the CPU code. It would be a bit different. If you have a GPU, by default, if you type pip install torch, it would come with CUDA 12.4 libraries. So it would support the GPU with CUDA 12.4. But if you want a specific version, you can also change it, and there are different URLs. And by the time you are watching it, there might be a whole new set of CUDA versions. So this is really specific in terms of what GPU drivers you support. But by default, you can also just do pip install torch, and it should technically work. Now, back to this one here, I'm also just double checking which version I'm using here. So here I'm using version 2.6. And I should say when I started writing this book, it was 2.0, because that was the most recent version 2 years ago when I started writing the book. But I tested the book on all subsequent versions of PyTorch, and I couldn't see any difference in any of the code. On the GitHub repository, I also have automated tests. So each time a new PyTorch version comes out, I'm just double checking it still works. And so far, I haven't seen any difference in PyTorch that would make any of the code different. So in this case, you can feel free to also use older versions of PyTorch, for example, 2.0, 2.1, 2.2, 3, 4, and 5. They should work equally fine. However, if you notice anything that doesn't work, for example, the results look different. You could just try also to install this specific version of PyTorch by doing pip install torch and then 2.6.0. And so this would then install this specific version of PyTorch I'm using right now at the moment. Okay, so this was a little detour. Maybe one more thing I wanted to mention is if you're new to PyTorch, it's essentially a deep learning framework. It's relatively comprehensive. It has a lot of things, but we are only going to use a subset here in this book. It's essentially more of a linear algebra library with a few deep learning convenience functions. There are whole courses and books about PyTorch if you want to learn about it. But if you want to learn about it efficiently, I also have Appendix A here. So I've been using PyTorch, I would say, since 2018 for 7 years now, and I've taught many PyTorch workshops, and I wrote another book about PyTorch and so forth. So what I want to say here is, over the years, I used PyTorch quite a lot, and I was thinking really hard, what are actually the parts you need to know for this book? And based on that, I compiled this Appendix A, which is essentially a book chapter of 40 pages approximately that just go over the essentials that you need for basic LLM training and development, where this should get you up to speed relatively quickly. Of course, if you're curious, I recommend considering a whole course or a book on PyTorch at some point. But if you just want to get up to speed with PyTorch for this particular book, try to read Appendix A, and maybe it's already sufficient. It might be a steeper learning curve because I'm trying to keep things efficient and compact, but maybe this is all you need at that time to really get up to speed, so you don't, let's say, go on a detour for a few months to try to learn PyTorch, and then, then you get maybe frustrated or get bored. So I would suggest maybe trying Appendix A, and maybe it's already sufficient to get you up to speed here. Now, back to the data loading. So we talked about PyTorch and importing PyTorch. Let's actually go back to section 2.6, data sampling with a sliding window. So we talked about the target word, predicting the next word. And so now we are going to prepare the data set accordingly. So we are going to take the input data and we are creating these chunks. And I mentioned before, we're using a chunk size of 4 or context size of 4 for visualization purposes, so it nicely fits into this figure and so forth. But in reality, these are usually larger, like 1024 in the case of the GPT-2 model. Or newer models use 8,000, 16,000 tokens in each row, but it would be hard, of course, to visualize here. And so, as you can see, the one box here, the left box, that's the input X that we are creating. And then the targets are shifted by one position, as you can see here. It's the same idea what I showed you earlier. We are just creating inputs and targets simultaneously from this text so that we can feed both to the LLM later when we are training the LLM. So let me actually do this in code. And for this, we are going to use a PyTorch dataset class. And so the reason why we're using a PyTorch dataset class is it will allow us to use the PyTorch data loaders later. And they are essentially a very nice and efficient way to create batches and to shuffle the data and to use multiple background processes to process the data faster. It has a lot of convenience added to it. So how a dataset looks like is we have a constructor here. We are setting them to empty lists. Then we are going to tokenize the text. So text is the input text we're going to pass. And so we get the token IDs. And here, this is the part where we are creating these so-called chunks. So these chunks are these two chunks, basically. And instead of, I should go back maybe one more time, instead of just creating one chunk for the inputs and targets, we're doing this for the whole data set. So we are storing these chunks here. We're adding them here for the inputs and for the targets. So we are appending them to these lists we created earlier. And it's the same concept as before. We are sliding over the input data set, and then the targets are shifted here by one position. So what we are going to do is we are taking this left box and we are going to slide it over the input. So you can see the first row is in the hard off. And then when we slide it over, The next one is the city stood the, and then old library and so forth. So it's sliding it over by one position. And it's, if you have a very large data set, it's maybe not the way to do it because you can't store 15 trillion tokens in memory. So this would run out of memory. But if you have just a few books, a few gigabytes or megabytes of data, I mean, if you have, I don't know, 1,000 books or something like this would conveniently fit. So you don't have to worry about it and over optimize at this point. There are a few more advanced ways and tools if you are really training LLMs on trillions of tokens, but for here educational purposes we are keeping things relatively simple and readable because this is the basic approach, and so to understand also how things work under the hood. Now we have this data set now, and I mentioned the data loader that we want to use. So let me, instead of typing all the code, just insert it below. So the data loader is created here, and I have a function I'm defining that returns this data loader. And so here we are defining the text. We can set a batch size, a max length of each context length. So before we set 4 is our length here. We can also, this is just a default parameter, we can override it later. We set the stride, it's by how many positions we are moving the box. We'll get back to that in a few moments. Whether we want to shuffle the data set, whether we want to drop the last batch or not. And this is actually an interesting one. This is really to avoid loss spikes. So for example, if we have a data set, let's say example 1, example 2, and so forth. If we have a data set like that, let me just do it like this. And suppose we have a batch size of 2. What the data loader will do is it will divide the data set into batch sizes of 2. But if the data set size is not divisible by the batch size, you often end up with very small batches at the end, the last batch, because it's the remainder. And this often results in loss spikes, like unstable training. So it's actually a good idea to always remove the last batch. If you do multiple epoch training, you also don't have to worry about missing certain data points by removing them. But also in general, usually data sets are so large that, if you don't use the last batch, doesn't really matter. So it's usually a good idea to have batches of the same size so you don't have these instabilities during training. This is why why I'm recommending dropping the last batch always. And then num workers is for using multiple background processes. I have it here set to 0 because I'm executing this in a notebook. And in some cases, this can be, might not work because notebooks are a bit more restricted than Python scripts in terms of spawning multiple subprocesses. Or if you're using Windows, I think Windows generally has some problems with multiple background processes in Python. So this is just like a safe choice, but you can try also to set it to a larger number, for example. But for these purposes in a notebook, this should be fine to set it to 0. And this was very conceptual. A few more things here. We are initializing the tokenizer. This is the tick token tokenizer we talked about earlier. Then we are creating the data set. That is the data set we have up here. And we are creating it with text, and text will be our training data set. And here is where we are creating the data loader using the settings I defined earlier, and we are returning it. So all very, very, I would say conceptual. So let's actually see it in action. And for that, we are going to use the verdict again, which is our short story that we downloaded earlier, the short story by Edith Wharton, raw text. So this is how it looks like. We have seen it earlier, and now we are going to pass it to our data set and data loader. So let me just, because otherwise it will end up a very long video, let me just copy and paste the code here. We are going to start with a batch size of 1 and a context length of 1 and a stride of 1. And so the batch size is how many samples are in each batch, essentially. The max length is our context length. It's how long the context here is, like the size of the box, how many tokens are in there. and then the stride is by how many places we are moving it. So for simplicity, I will show you stride of 1, and then we will change it. So if this is unclear, wait for a few moments. we will get to it, and whether we shuffle the data or not. And then we are iterating here just for demonstration purposes over the data set manually, and later I will show you a different way to do that. So here we are creating an iteration object, an iter object, and then we are taking the next sample from our data set. So when we are executing this, we can see the next batch here. So this is the first input. It only has a size of 1. And this is then the targets. So you can see the targets are shifted by 1 position. So, and then let's draw another batch. Now what you can see is that the targets here become those inputs. So the first one is always the inputs, the second one is always the targets, because that's how we set up our data set. So the first is the inputs, the second is the targets. Now you can see this is something where it's maybe not ideal, because when we have this input and then the second iteration has this input, there is an overlap. So these tokens are the same. And if you do it like this, the LLM sees certain tokens many, many times, and then it's kind of leading to overfitting. So what's actually better is to increase the stride by 4. So if we do that, you can see each of the tokens are unique. So you can see they are not overlapping anymore. And so what it does is it's moving this box by stride of 4 by 4 positions. So 1, 2, 3, 4, moving it by 4 positions. So we are at the city stood the. And you can see this is what's shown here in the second row. The reason why I showed you just the stride of 1 was so you can see that this actually works and it's not missing any data, because you can see this one picks up right here if we have a stride of 1. I thought this might be more intuitive, but if it is confusing, don't worry about it. Just go to the stride of 4, and then you have exactly what you can see here in the figure. Now, this is for a batch size of 1. When we are training deep neural networks, it's usually efficient to use a larger batch size. So what we can do is we can use a batch size of 8. So I'm just showing you a same thing here. Instead of batch size of 1, I have a batch size of 8, max length of 4, and a stride of 4. And then, some labeling so it's a bit more clear. And here you can see now we have the inputs here and the targets. And this is similar to what we are seeing here, where we have multiple rows, where each row is one training example. And so we have a batch size of 1, 2, 3, 4, 5, 6, 7, 8, and then the corresponding targets. Yeah, and this is really how we implement this data loader. And then later we can also iterate over it more efficiently. So this is a topic for later. I just wanted to set up this data loader so that we have one way later on to load the data into the LLM efficiently.
Get this book at Manning.com.